All right, let's talk about a sorting algorithm that sounds super technical, right? But what if I told you that you already know exactly how it works, and that you've probably used it hundreds of times without ever touching a keyboard? We're talking about insertion sort. Seriously, think about it. You've just been dealt a fresh hand of cards, and they're a total mess. What's the very first thing you do, almost without thinking? You start picking them up, sliding them into place, arranging them. That move, that instinct, that's what we're going to break down today.
If you've ever done that, then congratulations. You've already got the big idea behind one of the most fundamental sorting algorithms in computer science. That whole process of picking one card, looking at the cards you've already sorted, and finding just the right spot to slide it in, well, that is the heart and soul of insertion sort.
So here's what we're going to do. We're going to take that familiar card sorting feeling and turn it into something a computer can understand. We'll start with that analogy, then watch the algorithm work its magic, step by step. We'll look at how fast or slow it can be, explore a couple of its key features, and then, and this is the cool part, we'll see why this simple sort is still a huge deal in the software we use every single day.
Okay, let's really get into this. Picture it. Your hand is empty. You pick up your first card. Well, a hand with just one card is already sorted, right? Easy. Then you pick up the second one. You look at your first card and decide, does this new one go to the left or the right? Now you've got a perfectly sorted hand of two. Every single new card you grab, you just scan the ones you've already sorted and pop it into place.
And this quote just hits the nail on the head. It perfectly connects the algorithm to that real-world action. You build up your sorted section one piece at a time by inserting new things into their correct position. It's so intuitive, it's something we humans just do.
So that's great for us. But how does a computer do it? How does it take our human intuition and apply it to a list of numbers in an array? Let's translate our card game strategy into a set of rules a machine can follow. You know, the logic here is exactly the same as our card game. We pretend the very first item is our tiny, sorted list. Then, we grab the next item from the unsorted mess. We work our way backwards through the sorted part, shifting things over to make room until we find the perfect little spot to drop our new item in. And then, we just do it again, and again, and again, until everything is sorted.
All right, let's actually see this thing run. Here's our unsorted array. The algorithm looks at this and says, okay, the first number, 8, that's my starting sorted section. Now we grab the next element, the 2. Our job is to get this 2 into its proper place in that sorted section.
So first thing, we compare our new number, 2, with the last item in our sorted list, which is 8. Is 2 less than 8? You bet it is. So we shift the 8 one spot to the right to open up a space, and we slide the 2 right in. Perfect. See that? Our little sorted subarray just grew. It's now 2, 8. The rest of the array is still waiting its turn. So naturally, we move on to the next unsorted number, which is 4, and we do the whole thing all over again. We take that 4 and start comparing it backwards through our sorted list. Is 4 less than 8? Yes. So we shift the 8 over. Next, is 4 less than 2? No, it's not. So, we found it. That's the spot. We insert the 4 right there, between the 2 and the 8. You're starting to see the pattern, right? That sorted section on the left just keeps growing. It's 2, 4, 8 now. The next number up is 9. We compare 9 to the last sorted number, 8. Is 9 smaller than 8? Nope. Ha! Well, that was easy. It's already in the right place, so we don't have to do any shifting at all. Okay, now for a trickier one. We pick up the 3. Is it smaller than 9? Yep. Smaller than 8? Yep. Smaller than 4? Yep. Smaller than 2? Nope. Aha! We found its home. So we have to shift the 9, the 8, and the 4 all one spot to the right to make room, and then we pop that 3 right in after the 2. And for our very last step, we take the final number, 6. We compare it backwards. It's smaller than 9, smaller than 8, but not smaller than 4. So its spot is right between the 4 and the 8. And boom, just like that, the entire array is sorted. Every single element has been perfectly inserted into place. So we've seen how it works, but the next really big question is, how fast is it? And like a lot of things in computer science, the answer is, well, it totally depends on what you give it. Let's look at the two extremes.
And this is where it gets really interesting. In the absolute best-case scenario, the array has already sorted. The algorithm just cruises through, doing a single check for each item. We call that ON time. Super fast. But in the worst case, if the array is sorted in reverse,
Every single number has to be shifted all the way to the very beginning. The workload explodes. That's O(n) squared. And for a big list, that can get really slow, really fast.
Now, besides just raw speed, algorithms have other important traits. For insertion sort, there are two you really need to know. It's what we call in place and stable. First up, in place. All this means is that the algorithm is really good with memory. It does all of its sorting work right there inside the original array. It doesn't need to create a whole new copy of the array to work with, which some other algorithms do. It just needs one extra little variable to hold the number it's currently inserting. That's it. It's very efficient. Second, it's a stable sort. Now, this is a bit more subtle, but it's really important. Let's say you have two number 5s in your list, but one is colored red and one is blue, and the red one comes first. A stable sort guarantees that after sorting, that red 5 will still be before the blue 5. Their original order is preserved. And insertion sort is stable because it never shifts an item past another item that has the exact same value.
Okay, so you might be thinking, if its worst case is so slow, why do we even bother with it? Why is this thing so important? Because in the right situations, this simple little algorithm isn't just easy, it's actually incredibly smart.
This is where insertion sort becomes a secret weapon. For really small arrays, its simplicity means it has almost no overhead, making it one of the fastest options out there. And it's an absolute speed demon on lists that are already mostly sorted. This makes it the perfect tool to be used inside more advanced, hybrid algorithms. TimSort, for example, the algorithm that powers sorting in Python, uses a more complex method for the big picture. But when it breaks the problem down into small chunks, it switches over to insertion sort to finish the job efficiently.
But you know, maybe its biggest value isn't its performance at all, but what it teaches us. Insertion sort is a fantastic first step in understanding how algorithms work. It gives us a really clear picture of core concepts like loops, making comparisons, and this idea of building a sorted section piece by piece. These are the fundamental skills you need before you can tackle the really complex stuff.
So in the end, insertion sort leaves us with a pretty cool question that goes way beyond just programming. It reminds us that fastest isn't always best. For the right kind of problem, a small list or one that's nearly sorted, this simple, intuitive approach is the perfect tool for the job. It's a great reminder for all of us to stop and ask, when is the simplest solution actually the most brilliant one?